Previously, we've discussed a method of exploring a graph in what's called breadth-first order, an order whereby from any given node we explore all of its adjacent nodes before we explore any other nodes. We saw that that was useful for finding shortest paths in a graph. We're now going to explore another order of exploring a graph called depth-first search. So here, if we're at a node, we explore only the first node adjacent to it and move on to its first adjacent node and move on from that node to yet its first adjacent node and so on before we ever look at the second adjacent nodes of any of the previous nodes. That is to say, we search as deeply as possible first. There are quite a number of applications of this order of search. Two examples, I'll give you two examples right now. In the first example, each node represents a task to be done, and a directed arc from one node to another says that the first task must be complete before the one it's connected to can begin. These, of course, may be cascaded so that if A needs to be done before B and B needs to be done before C, we'll have an arc from A to B and one from B to C, but not necessarily one from A to C. What we're after in this problem is a linear list of tasks that's legitimate. That is to say, we're first going to do one task, and then we'll do the next task, and then we'll do the third task, and then we'll do the fourth task. That's a linear order. And we want this linear order to satisfy all of the constraints in the directed graph. That is to say, that so that we never do a task before its precursor tasks are complete. In another application, we have a directed graph, and we can think of it as having portions that are called strongly connected components. A strongly connected component has the property that in that portion of the graph, if you start at any node, there exists a path, not necessarily of length 1, that gets you to each of the other nodes in that portion. If a graph might have a second strongly connected component in which you can get among those nodes by paths, but you can't get from all of those back to the ones in the first connected component. And so on, so that each connected component is as big as it can be, such that you can get around from anywhere to anywhere in each connected component, but and that there can be connections between these portions, these strongly connected components, but not in such a way that from within any given connected component you can get to all of the nodes of another connected component. Now let's look at an example to get a better understanding of how this depth-first search works. We have this directed graph of 6 nodes. Notice that the directed arc, there can be directed arcs from a node to itself, as is the case with node Z. We have some node that's designated as the starting node. Here we will talk about it being node U. U has two nodes that you can get to that are adjacent to it, V and X. But let's say V is the first one. So we march from U to V, mark the path U to V as an arc in this depth first order, and now we're at V. And rather than looking at anything more from U, which we would have looked at for breadth first, we're at V and we're just going to look on from V immediately. So V is connected to Y, and so we take that step. V to Y is shown in item C of this diagram, of this graph. Now we're at Y. Where can we go to from Y? Well, we can go, the only place we can go to from Y is X, so we'll go continuing in depth to X. So now we're at X. This is stage D. We look at where we can go to from it. We can go to V, but we've already been there, so we will not go there. We don't go to unexplored places. As a result, we're going to say we're done with X. We've explored all the places that you can get to from it, and we don't have to look at them anymore, so we'll blacken it as shown in number F, and then we backtrack to Y. And we look at the other places we can get to from Y other than the one we explored. And there aren't any. So we mark that as complete in item G of this diagram. And then we backtrack again to V. And there's nowhere more we can go to from there, and so we mark that as complete. And backtrack along the path to it, to U, and U has an arc that we haven't looked at, namely to X, but X is complete. And so we mark U as complete. We see that in item J. And we've now explored everything that we can get to from our initial starting point of U. But we haven't explored the whole graph, so now we have to pick a new starting point. Let's say it's W. It's the next unexplored node that we have in our list of nodes in their order U, V, W, X, Y, Z. From W, we find we might first see the arc from W to Y, but Y is already explored. Indeed, it's complete. So we move on to the next arc from W, which goes to Z, and mark that one as being an arc. As we see at stage M in the diagram. From now we look at Z. We say, where can you go to from Z? Well, you can go to itself, but itself has already been marked as explored, so that one doesn't count, so we're done with that. So we can backtrack along the path that came to it, which is back to W, and W has no more arcs to unexplored places, and so it gets marked as complete, and we have, therefore, all the arcs marked as complete, and we've completed our depth first search. Now, there are other aspects of this diagram, namely the numbers that are inside the nodes and the labels on some of the arcs as F, B, and C, that we'll cover later. But for now, all we need to know is that this is the order in which we do depth-first search. So, in depth-first search, we explore an edge out of the most recently discovered vertex, and later explore other edges of that vertex, but not now. Having explored those edges, we go to a newly discovered vertex, if there is any, and that becomes the most recently discovered vertex, and so on. We saw that when all of the edges of a vertex have been explored, we backtrack to explore other edges leaving that vertex. Okay, we call the node that from which we came to node V its predecessor. The idea is, as in this, we are searching as deeply as possible first. In the depth-first search algorithm, when once a vertex V is discovered, during a scan of the adjacently list of some already discovered vertex, the depth-first search algorithm records this event by setting a predecessor pointer. That is to say, if U pointed to V, we set pi of V, the predecessor of V, to be equal to U. So the coloring scheme that we used here is the same as breadth-first search. We have unexplored nodes. Once they are initially discovered, we make them gray. When they're complete, we make them black. We can look at this predecessor subgraph that the grade over arcs that this produces. We'll call that G sub pi of V and E, where the edges among V, which are not all of the original edges, but a subset that we'll call E sub pi. The predecessor subgraph forms a forest, a collection of trees. We saw in our example that the first four vertices of the original graph formed one tree, and the remaining two formed another simple tree. And these edges that were grayed over, namely they were the edges that were the first ones to get to a node that had not been previously discovered, they're called tree edges. But in addition, we saw that each vertex had two timestamps in it. What is time? Well, following an arc increments our time. So we start at time 1. When we follow an arc, we get to its first adjacent element at time 2. If we follow another arc from it, we get to that vertex at time 3, and so on. And so the discovery time, D of U, is the time when the vertex U was first discovered, when it first was made gray. We also have the other timestamp when at what time we have established that we're complete. We've made it black. And as a result, D of U is less than F of U. We discover it at a time before we make it complete. Let's look at our example again. Now that in A, we looked at U first because it was the first in our vertex list in order. And we say we entered it at a time 1, but then we moved along its first arc to V, and we increment our time so that we're at time 2. And at the next stage, we went from V to Y, and so that gets labeled as 3. Entrance time 3, discovery time 3, and then we go to X, and it's seen at discovery time 4. And then, having discovered it, we find out that there are no further arcs. But looking at the arc list increments our time clock. So at time 5, we've decided that there are no other arcs that are to undiscovered nodes, and so we're at time 5. And so X has been labeled as complete, and it said it was discovered at time 4 and completed at time 5. Then we backtrack from X back to Y. That takes us a time unit, and so and discover that there's no more arcs for it to do, and so we label its closing time as time 6. Repeating the backtrack to 2, we see there's nothing more for it to look at, so that's time 7. We backtrack to U and close it because there's no more arcs for it to follow to undiscovered nodes. And so U was discovered at time 1 and complete at time 8. We increment our clock, since there's no arcs left to explore from the ones we've already discovered, we go on to the next undiscovered node in the list, even though it's not connected to anything. So we enter W at time 9. We enter Z at time 10. We complete Z at time 11, and we complete W at time 12. So we've seen these start-stop parentheses in each node. So node said we started looking at it at time 1 and we finished looking at it at time 8. That's what 1/8 means. And for example, for node Y, we know that we started looking at it at time point 3 and we ended looking at it at time point 6, and so on. So here is the algorithm that we've created. We have a loop over all the vertices in the list V of this graph. For each of the vertices, we initialize them by being white, undiscovered, and we set their predecessors to nil, and we initialize time as 0. So I have one loop to initialize, and now we have another loop from 5 to 7 that says we pass through U in the list, and if it's white, that is to say, if it's undiscovered, then we visit its adjacent ones. And we have, in the next slide, we have the DFS visit algorithm. When we visit a node, U, the first thing we do is gray it. That is to say, label it as having been discovered. We increment the time and then put that as the starting time for that vertex. Then we look at all the vertices that are adjacent to it. And in that loop, if the node that's adjacent is undiscovered, it's white, then we let the predecessor of that node be U. And in the depth first order, we then visit V. That is to say, the node adjacent to U. After we have gotten through all of the nodes adjacent to U, we're done with U, and so we color it black. And we set its finish time to 1 beyond. We increment the clock and set it as the finish time. This is the complete visit algorithm, which of course is used in the general depth first search algorithm. We need to analyze the running time of DFS on a graph with V, big capital V vertices and capital E edges. The original, the main algorithm that's called DFS starts with clearing all the nodes, making them all white, and that takes theta of V time. And then visiting all the nodes that have not yet been discovered, which can take as much as time proportional to V. For each white vertex, when it's painted gray the first time, the lines 3 to 6 of the DFS visit algorithm is executed as many times as this as the node has adjacent elements. But that only happens once. So the total cost of executing DFS visit through all the times is the sum of the count of the adjacencies, and that's E. That is to say, that part, the DFS visit calls, require all of them together take theta of E time. The result then is that the total running time of DFS is theta of V plus E. Note, by the way, that it's possible to have E be theta of V. That is to say, for example, that if you have on the average one edge per vertex, then you would have the same number of edges as vertices. It's possible that E is a good deal less than V. We may have many, many vertices, but broken into parts, and there are way fewer connections than vertices. So E could be, for example, order V to the half. Or it's possible that there are many, many, many connections. Of course, E can't be more than order V squared, because that's the number of possible branches, but E could be order V squared. It could be a half V squared. So theta of V plus E, if E was theta of V would be theta of V. Theta of V plus E, if E was theta of V to the half, would be theta of V, and theta of V plus E would be theta of V squared if E was theta of V squared. Return to our example in which we have recorded all the start and stop times. So we see at the end in P that node U started at time 1 and ended at time 8, V at 2. It began at 2 and ended at time 7. And likewise for all the other nodes. The point is that if we go from some node, let's say U, to some other node, let's say V, it starts later, and moreover, we'd never backtrack until we complete, so it ends sooner. V ends sooner, and then we backtrack to U, which ends at a later time. This causes these times to form a parenthesis structure. That is to say, U's parentheses are at time 1 and 8, and they include V's, which were from 2 to 7, and those include V's, which were from 3 to 6, and those include X's, which are 4 to 5. And moreover, W's, which are 9 to 12, are not included within any of the previous ones. But Z's 10 to 11 was included within W's parentheses. This parenthesis structure is the topic of this slide and the next. DFS produces this predecessor subgraph. That is a forest of trees. Each one of the groups of vertices that you could get from the beginning vertex for that group to the remainders forms a tree. But as we saw in our example, we could get to the first 4 vertices from the originally first one, and that produced one tree. And then we had to go on to the next available undiscovered node, not via an arc, but by the fact that it's next on the vertex list. And from there, another tree was formed. And this can go on for as many subtrees. So you end up with a forest of trees. The second property that we will want to discuss is that these discovery and finishing times have a properly nested parenthesis structure. This will become clear in the figures that we'll look at now and the theorem. Let us take this 8-vertex graph as our example, with our starting node being S. It takes 16 time steps to pass through this graph. We pass from S to Z, and from Z to Y, and from Y to X. And then we have to backtrack to Z, and then we pass from Z to W, and then we have to backtrack again and again until we find that we're done with the 5-element subgraph consisting of S and the 4 that are to the left of it. In which case we move on to T at time 11, go from T to V, and then we have to backtrack and we go from T to U, and then we're done with T. So we've produced 2 subtrees as marked in item B. That is to say, we have the tree that has X and W as its leaves. X is connected to Y. W is connected directly to Z. Y is also connected to Z. And that was backtracked to S. And so we see the subtree on the left in B. And likewise, we have a subtree from starting T at time 11 and going respectively to V and to U. And if we look at at this graph, we see that S couldn't complete until all of the things that we had reached from it were done. So it took from time 1 to 10. And the thing we went to from it could only have started after it. In fact, it started at time 2. And had to be complete before we backtracked to S. So it went from time 2 to 9, strictly a sub-range of S. And Z went to both Y and W, first Y from times 3 to 6, and it could only go on to W once it was finished looking at Y and then X, but it couldn't complete until all of 3 Y and W that it could go to were complete. And so we have that Y goes from time 3 to 6, W from time 7 to 8, and both of those are part of the range of Z, because Z had to start before we could get to Y and W, and had to complete after we had done Y and W. Similarly, Y went to X, and X had to be complete at time 5, had to begin at time 4, that was parenthesized within the Y times. That is to say, was an explicit subrange of the time for Y. We see the same behavior with regard to T, going from 11 to 16, and having subranges 12 to 13 for V and 14 to 15 for U. So we have this parenthesis structure. These examples of the parenthesis structure suggest this theorem. indeed these properties that we've seen hold are what this theorem says. If you have a pair of vertices, any pair in a graph, vertices u and v, we have the parenthesis of u and the parentheses of v. That is to say, du to f of u, beginning to ending time of u, and beginning time to ending time of v. There are only three possibilities. One is that they're entirely disjoint. That is to say, there's no overlap between d of u to f of u on the one hand and d of v to f of v on the other. That was the case for the parentheses in the left subgraph in our example, and the parentheses for the right subgraph, the one that formed the first tree in our forest, predecessor forest, and the ones that formed the second one. Okay, if they're not disjoint, then it either has to be that one is outside and the other one inside it, or vice versa. That is to say, the two possibilities are u's parentheses are entirely within v's, or v's are entirely within u's. Example. We have a graph here with 7 vertices, A, B, C, D, E, F, G. And starting at A has the interval 1 to 10 because in depth first order it moved to T to B, which had interval 2 to 5, and within that C it moved to C, which had interval 3 to 4, backtracked to B, backtracked to A, and then within the 1 to 10, the interval 6 to 9 of F, and then 7 to 8 of G within that, and then with no further way to get to anything from the original A, move on to D, which has intervals 11 to 14, within which there's 12 to 13, which is the E. We see that the D to E parentheses have E's parenthesis within D. That is to say, 12 to 13 is within 11 to 14. And that's completely separate from the 1 to 10 in A. You'll notice also in some of the previous graphs and in this one that some of the edges are labeled F, B, and C. We'll be talking about those labels on graph edges. So what we've said is that according to this theorem, V is a proper descendant of U in the depth first forest if and only if its parentheses D of U, if the parentheses D of U to F of U contains the parentheses D of V to F of V. Moreover, in a depth first forest of a graph, the vertex V is a descendant of U if and only if at the time D of U, which is the time that the search discovers U, the vertex V can be reached from U along a path consisting entirely of vertices that have not been darkened, that have never been moved along. We can prove this by the nesting theorem. The parenthesis theorem will produce a contradiction. Here's a worksheet question for this first part of the depth first search algorithm video. There'll be another one at the end of the video. Put the two of them into a single worksheet that will be passed in as a single item to be passed in. And here is an exercise on creation of a depth first search structure. That is to say, exploring a particular graph where the vertices are listed in alphabetical order. That is to say, starting with Q, then R, and so on. And you are to compute the starting and ending times, and also to show the parenthesis structure. We now move on to some applications of depth first search. In some of these applications, it's useful to have the edges in the graph classified into types. We've also already noticed that there are edges that form the depth first search predecessor tree. We color an edge when we're at some vertex, let's say U, and moving along that edge, we first discover the vertex at the other end of that edge. That is to say, it was white when we arrived. In that case, we color the edge, and since this edge will be part of that tree, we call it a tree edge. In other situations, we are at a node and we look down an edge and we find that it's still gray. It's gray though, meaning it's been discovered, but the fact that it's gray and not complete means that it was our ancestor. If it was gray and not our ancestor, it would have been made complete. These edges produce a cycle in the graph, and we call them back edges. In other situations, we look down an arc, down an edge, and we find that the edge is complete. That means we've been down to it and finished it and then came back up to where we are. And so it's our descendant. And the edge, the new edge from us to it, that is to say an edge from the node we're working on to a black edge, is an edge to a descendant, possibly around other intermediate descendants, and we'll call that a forward edge. And any other edge that isn't either tree or back or forward we'll call a cross edge. In the graph we were working on earlier as an example, these edges are shown. So you see in item D, we've gone from U to V to Y to X. And then and each one of those is gray. And when we're at X, we find that we have an edge to the gray node V. This says we have a cycle from V to Y to X and back to V. And that edge back to this gray edge from X is therefore labeled as a back edge B. The colored edges that we've seen being created so far from U to V, from V to Y, and from Y to X are all tree edges. Moving on to item I, we see ourselves having backtracked to U, and then we find an edge from U to X, which is black, that is to say complete. This is a forward edge, an edge to a black. It does not create a loop. It just creates another way to get to something that we've already got to by going U to V to Y to X in depth first order. And so we label that as a forward edge. In item L, we see the creation of a cross edge. It's an edge from W to Y that is indeed to a black edge, just as with forward edge, but the edge Y is not our descendant, and we can tell that by the parenthesization. And so we label this black edge as neither forward nor back nor tree. It's a cross edge. It takes us across from the subtree WZ to the subtree to the tree W and Z, which is part of the forest of trees, to the other tree in the forest made from U, V, Y, and X. To summarize our algorithm for edge classification, we can modify the depth first search algorithm such that when we look down a particular edge, if the target is white, the edge that came to it is a tree edge. If it's gray, it's a back edge. And if it's black, it's either forward edge or a cross edge. And we can tell a forward edge from a cross edge using the parenthesization properties. So far, we've been looking at directed graphs. But we can do depth first search on undirected graphs. In undirected graphs, there aren't any forward edges or cross edges. Every edge is either a tree edge or a back edge. We will be shortly looking at an application called topological sort, and we'll be also looking at other applications, and this property will be important in understanding why they work. The application that we're moving on to is called topological sort. The idea is that we have a graph with precedence requirements. That is to say, for example, there's a list of tasks, and a particular task, which is a task in each vertex, and that task has will have certain arcs from it. Those edges are things that it's explicitly a prerequisite to. So, for example, we expect to put on our undershorts before we put on our pants. Of course, some tasks will be prerequisites to other tasks that are in turn prerequisites to yet other tasks. And what we'd like to be able to do is, since we can only do one task at a time in this situation, is to get a linear list of tasks that satisfies these prerequisite or precedence requirements. So at the bottom we see such a linear order. Put on your socks first, then your undershorts, then your pants, then your shoes, then your watch, then your shirt, then your belt, then your tie, then your jacket. That's a linear order, and we want to discover such a linear order that is okay with respect to this precedence graph. Notice that it makes no sense for the original graph to have cycles, because then we'd have to do A before B before C before A if there was a cycle A, B, C, A to B to C to A, and that doesn't make any sense. So the input to topological sort has to be a directed graph. The direction tells us which goes before what, and also acyclic. About these types of graphs that are called directed acyclic graphs. They arise in many applications where there are ordering constraints. The idea is that the graph is tree-like, but not a tree. It's tree-like in the sense that each vertex can have none or one or multiple children, that is to say, things that have an arc from it to them, but that after that you can't get back to the original arc. There's no cycle. It's different from a tree in that a particular node, a particular vertex, can have multiple parents. The input to a topological sort must be a directed acyclic graph. To restate the topological sort problem, we're given a directed acyclic graph, a DAG G, with vertices in the set V and edges in the set E. And we desire a linear ordering of that DAG such that if UV is an edge, that is to say U must precede V, then U appears before V in the ordering. We've said that there need not be a unique solution to topological sort. Here's the algorithm. We simply use depth-first search, and in the process we compute the finishing time for vertices. Each time we finish a vertex, we insert it onto the front of the linked list. And this linked list, when we finish, is the order, the result of topological sort. So when we finish, when the very first item to be finished, very first vertex to be finished, does indeed finish, that goes into the linked list first. The linked list is initially empty. Now this is in. Then the next one to be finished is linked before it, that is to say, from it to the one that was in the linked list. And at each time we finish one, we put it at the front of the linked list, linking to what was already in the list. That's the algorithm. Let's see it work. This is the example we saw earlier. If we start our depth-first search at an arbitrary place, let's say shirt, we find ourselves going from shirt to tie to jacket and then backtracking. And in the process, we close jacket at time 4. Therefore, jacket goes on to this list first, that is to say at the far end. We then backtrack to tie and finish it, and so tie gets on the list. We backtrack to shirt, but we're not done. We go on to belt, finish it at time 7, and so belt goes on the list next. That is to say, earlier, before tie and jacket. We come to shirt, and shirt's done. And so we put shirt on the list. Now, we need a new thing off the vertex list. Let's say we get watch. Watch has no links from it, so it's completed and therefore put at the front of the list. We need now, again, a new item from the list. Let's say it's undershorts. We look at undershorts. It takes us to pants. Pants takes us not to belt because that's already been closed, but on to shoes. Shoes has no further arcs from it, so it's finished, and we put shoes, therefore, at the front of our linked list. We backtrack to pants and finish that. Gets put on the list, then undershorts. We finish that, and then we still have one item that we haven't yet explored, which is socks. We finish that, and socks gets put on the list. it ought to be reasonably intuitive why this is going to work. The point is that if we get to a particular place and finish it, the things that preceded it could not have been finished. Where we do with the same graph, we do the depth first search in a different order. And when we do that, if we start with undershorts and then later do, after we finish all the places we can get to from that, we do shirt, and then after we finish that, then we do socks, we'll get a different linear order. Both orders are legitimate. So in this particular ordering, the order would be jacket, which is closed at time 5, followed by belt, closed at time 6, followed by shoes, closed at time 8, pants at time 9, and undershorts at time 10, and then tie at time 13, and shirt at time 14, and socks at time 16. So essentially this is a sort in the sense that this thing produces a sort in the order, in the reverse order of finishing time. The largest finishing time first, the smallest finishing time last. Sort, take, well, the first step was to do depth first search, which takes time order V plus E, the number of vertices plus the number of edges. Each insertion is one insertion per vertex. The insertion itself is order 1, so that the total insertions take order V time, and therefore the topological sort is a theta of V plus E time algorithm. Here is the algorithm itself, where the depth first search is embedded within the algorithm. We empty the linked list, color all the vertices white, and then begin our search somewhere. The first item in the capital V list. We do the depth first search, and as we get completions, we append the completed node into the front of L. The second question for your worksheet, pass in the worksheet with the previous question plus this one as a single assignment to be passed in. We have the second exercise that will be done in the inverted class. This is the same graph that you did depth first search on. You did that depth first search with the assumption that the original vertex list is in alphabetical order, Q, R, S, T, and so on. But this time, label the edges as tree edges, back edges, forward edges and cross edges. Remember that back edges make cycles. And thus, what I want you to do is to form a DAG by taking this graph and removing any cycles. With that result, you should create a topological sort of this modified graph, showing the result and saving it for a future exercise, because we will see that topological sort is a prerequisite or a subroutine for yet another important application of depth-first search. Once you have created the linear order, make sure that for the tasks T, R, and W, that the tasks for which they are prerequisite or pre-prerequisite are accomplished in order, as well as that the tasks that are prerequisite to it, each one of them, are done by the time you get to the task T or R or W.